Today we're going to be talking about section 9.4, which is on ellipses. Now, in our previous section 9.3, we talked about circles, and we said circles were defined as an infinite number of points that were equidistant from one point, and that equidistant was our radius, and that one point is the center. Ellipses are a little bit different. It's another conic section, but in this case we have a bunch of different points that have special names, special values. So let's look at some vocabulary now. Now, an ellipse is actually defined as the set of all points that are the sum to one value, and that one value is called the focus. Okay. Now we have two foci, plural focus. We have two foci in every ellipse, and the foci, or every point along this line right here, there's four sets of those quadrants, but every point along there is equal to some value, okay, right here. So we have A, we have the value of A, okay, from the focus to, we call the covertex, 0B, and we have the value from the center to our covertex is also value B, right? And so what happens is we end up having this, basically this formula that forms A, B, and C all together that hold them accountable to each other, okay? And we're going to look at that on the next page. Now, let's talk about some points on here. Now, we said that we have our foci, okay, which in this case, we're looking at a horizontal version of an ellipse. Okay, so we have our foci, okay, at negative C0 and C0, okay. We also have two endpoints, okay, we call these vertices, and the distance from vertex to vertex through the center is called the major axis, major because it's longer. We also have a minor axis, and that's the value through the center from our co-vertices, okay? And obviously this one has a center, right? Here on the bottom, we're looking at an example of a vertical ellipse. Now in this ellipse, same deal, has a center, has two foci, okay? It also has a major axis, but now you'll notice that the major axis, the longer of the two, is this way, okay? And we also have a minor axis going across, okay, from covertex to covertex. Now, let's look at some important information, okay? So some important information about this. First, the equation of ellipse centered at the origin. Now, since we have two different versions, horizontal and vertical, we have to have two different standard forms of our ellipse. So we'll look at the first one. We're looking at the horizontal version. So you look in this equation, the horizontal, I notice that I have x squared over a squared plus y squared over b squared is equal to 1. Okay? Now, what is a? Well, a is half the distance or half the length of our major axis. So from the center, we said on our last example, the center to a, okay? So from the center to a, that's the value of a, right? We also said that we have a b, okay? And that's half the distance of the minor axis. So from the center to b is going to be b. We square that, and all of it is equal to 1. Now, I can also tell a horizontal ellipse by its foci. You'll notice the number that changes on them is the x. The constant is y. Okay, so in this case, it's 0 since it's centered at the origin. Now let's look at a vertical ellipse. Okay, one of the long ones. Same sort of thing. Our equation is very similar. But what you notice is that this time, y comes first. Okay, so we have y squared over a squared. A squared is still the first one. Plus x squared over b squared is equal to 1. Our foci, the number that changes is our y value. Okay, so if we see that the foci changes for y, we know that it's a vertical ellipse. A is still found by looking at it's half the length of the major axis, and b is still half the length of the minor axis. Now, I said on the last page that that our foci was set up by some formula. It's this equation right here. C squared is equal to a squared minus b squared. Okay, so that's the value that changes all the time. Okay, and so if we know a and we know b, or if we know b and we know c, we can always find the third one by using this. Looks very similar to the Pythagorean theorem, but it is different in ellipses. Okay, all right. So let's look at an equation. All right, so we're going to look at this one right here. Now, we know a couple different things. First off, we know this is a vertical equation or vertical ellipse. So we know that y squared comes first. Okay, so we're going to write that y squared plus over something plus x squared over something is equal to 1. Remember, all ellipse equations are equal to 1. Now, I need to know what a is. So a is the distance from the center to my endpoint right here. And so we notice that since our major axis is the longer of the two is up and down, we know that the distance from the center to one of the endpoints has a value of 9. And so that means I know that a is equal to 9. So here, this is going to be a squared, which is 81. Now, the next question is, what is b? Well, they don't tell us what b is. Okay? It's some value right here. They don't tell us how long the minor axis is, so we can't figure it out that way. But we do know that c, our foci, is 7 from the center. Okay? And so we said that we always had this formula. C squared was equal to a squared minus b squared. So let's set that up to figure out our missing value. So we said c squared was equal to a squared minus b squared. I know what c squared is. C squared is 49 because 7, actually, I'll write it like this. I'll do an extra step. So 7 squared plus 9 squared, or excuse me, is equal to 9 squared minus b squared. So I don't know any idea about b, but I know that c squared is 7, or c is 7, and I know a is 9. So now I'm actually going to square these numbers. And I get 49 is equal to 81 minus b squared. So how can I figure this out from here? Well, if I want to figure out what b squared is, there's a little bit of math involved, but basically ends up going like this, right? I can subtract 49, okay? And when I do that, I can also move b squared to the other side by adding it. So plus b squared and plus b squared. So you'll notice this pattern. When you do it long enough, you'll notice that this ends up happening. B squared is equal to 81 minus 49, or a squared minus c squared. All right, so I subtract those two numbers, and I find that b squared is equal to, let's see, 32. And so b is going to equal the square root of 32. And I'm going to leave it as a square root because what ends up happening is in our equation, I need to square it anyway, right? So b squared is just 32. And so here's the equation of our ellipse, okay, centered at 0, 0, that has a foci at 7, or foci distance of 7, and a major axis, half of it being 9. Okay. So on the bottom here is a problem that you could do. It has vertices at -4, 0, and 4, 0, and has co-vertices at 2, 0, or excuse me, foci at 2, 0, and -2, 0. Now, let's say that we're looking at the equation of an ellipse that isn't centered at 0, 0. And so just like we talked about when we looked at circles and when we looked at parabolas, we have an h and a k, h and k being our center, right? And so the same thing happens. A horizontal ellipse looks like this. It's x minus h squared over a squared plus y minus k squared over b squared is equal to 1. Again, notice, still equal to 1. A squared is still first. B squared is still second. We also notice that our foci, still the x is what changes, okay? And in our vertices and co-vertices, right? In our vertice, h plus some value of a, and in our co-vertice, it's k plus or minus some value of b, right? And we can figure this out. Sometimes it's easy when we graph it, but sometimes we don't need to graph it. We can just look at it algebraically and figure out our values of a, b, and c, right? We also notice that vertical, same thing, y comes first, a squared is still bigger, x minus h squared over b squared, still equal to 1, okay? All right, so we have an example here on the bottom that actually we can look at. We notice that that instead of being centered at 0, 0, we now have a center at 4, -5, but we notice that the whole ellipse changes location. It doesn't change anything else about it. It just changes, it doesn't change the length of the major axis or minor axis. It doesn't change the distance from the center of the foci, doesn't change any of those things. The only thing it changes is where it's located, right? And we can use that to our advantage. Okay. All right. So let's write in the equation of an ellipse with vertices at 6, -8, and 6, 4, and co-vertices at 3, -2, 9, -2. And we can actually figure out our center. Doing these long enough, I can show you a hint, but doing these long enough, you start noticing the same sort of thing. The first thing you notice, I had 6 for both my x's of our vertices, right? I notice that my co-vertices, I have y that changes or stays the same at -2. So using that information, right, how do you think we can figure out what our center is? Well, what ends up happening is our center, HK, ends up being 6, -2. It's the two things that remain the same. In our two vertices, x is the same. In our two vertices, y is the same. Okay? So we now know what h and k are, right? We can also use that to find the length of A and the length of B. All right? So if you think about it, if we look at our vertices, right? Since the x remain the same and the y changes, we know that this one is going to be horizontal. Now you might be asking, how do I know that for sure? The way I know that for sure is if x stays the same, let's say we graph this, right? Right? So let's say the x stays the same. Let's say that this goes by 2s and this is 6, and so going up by 2s is here, and then going down here it's here, right? You'll notice that the 2 points that I graphed are right on top of each other, and they are longer. That's the major axis. Our minor, it says, is at 3, 3, -2, so down here, and at oh, whoops, mid-6. Sorry, +6, and then down here. Okay, so these 2 points are. I don't want something negative. Anyway, okay, so you'll notice that this again is going to go kind of like this. It's for sure a horizontal ellipse, right? Centered at 6, -2, which we can tell. The center of this one's going to be 6. The center of this one's going to be -2. So we know our center for sure is there. Okay? So if we know those things, right, and we know that this is vertical, it means y comes first. So I'm going to do y minus our k, which in our case is -2 squared over a squared. So what is the distance, basically? What is the distance from -8 down here to +4? Okay, so what's the distance there? And so we're just going to take 4 minus -8, which ends up being 12. So that means that if the whole major axis is 12, half of it is going to be 6. And so that means our A value is going to be 6. And so in our equation, 6 squared is 36. Go to the next one. Okay, we know that x comes next. It's x minus 6 because it's centered at 6. And then we need to find the value of B. Okay, well, again, the distance from 3 here to 9 here, 3 to 9, or 9 minus 3 is 6. So half of the minor axis, half of 6 is going to be 3. And so we know that B is going to be 3. And so down here it's 3 squared, which is 9. And all of that is equal to 1. So here's the equation of our ellipse. Here's a guided practice problem that's looking at an equation. Vertices are at -3, 8, and 9, 8. Co-vertices are at 3, 12, and 3, -4. So hopefully, by our little trick, we can figure out where the center is, and we can write the equation of our ellipse. Good luck on the next couple questions, and we'll see you for the next part of section 9.4 tomorrow.